Hi everybody. So we continue the story of coadjoint orbits, and I would like to start with a small remark on the Kirillov character formula. First of all, let me write a somewhat more abstracted, somewhat more precise formula in the semi-simple case. So let's say G is semi-simple. And lambda is a weight of G. And let's say rho lambda is the highest weight representation of G with highest weight lambda. Somewhat confusingly, we denote also by rho, but without any subscript, the sum of positive roots. And then in this case, a somewhat more precise version of the Kirillov character formula says that J1/2 times the character of the representations is equal to the integral over the coadjoint orbit of the point lambda plus rho. You see, last time we had examples where there was a shift of weight by 1 from m to m plus 1. So that's the more general formula with this shift. And here that's the standard orbital integral. So, so that's a more precise formula, but with all the warnings, they're still true that I gave you last time. So here maybe just one more point that D to D is the dimension. Is the dimension of the orbit. Now, maybe let me also introduce the notation I lambda plus rho of x. So very pleasantly today, I can have parallels, some parallels with the mini course of Marcus, and also with some of the short talks that we heard yesterday. And you know, Marcus explained to us that instead of asymptotic formulas, we should be looking for exact formulas. And well, I'll be doing exactly the opposite. So the Kirillov character formula, albeit maybe sometimes it's true, sometimes it doesn't make sense, and so on. But it's an exact formula, right? The orbital integral is proportional to the character with some fixed function. And now I would like to have something weaker. I would like to reduce to an asymptotic formula. So let me introduce the following idea of scaling, which will work for us later today. So I will be multiplying the weight by some large positive integer, let's call it capital N, and I will be dividing the Lie algebra element by the same integer. So basically here, the group element gets closer and closer to 1, and the weight becomes bigger and bigger. And in this case, there is the following fact, which you can in principle derive from the Kirillov character formula, but it's a weaker statement. So the character of the scaled group element now behaves asymptotically when capital N goes to infinity. And now I at least partially fix those factors of 2 pi. You know, I always have factors of 2 pi wrong. 2 pi, sorry. So N over 2 pi. to the power d, where d is half of the dimension of the orbit, times I lambda of x. So, so that's the asymptotic behavior of the character when n goes to infinity. And in fact, it will behave with n, so there will be subleading corrections, say n to the power d minus 1 and so on. But that's the leading contribution. And the leading contribution is n to the power d, where d is half of the dimension of the orbit. And you see here, it's also funny, instead of lambda plus rho, right, there was this kind of non-trivial correspondence between representations and coadjoint orbits, right? We were saying that the character formula needs some correspondence between weights and coadjoint orbits. And in this case, you see there was that interesting shift by rho, but now in the asymptotic formula, we can ignore it and we just put here I lambda of x. So here the correspondence becomes very, very simple. To the weight lambda corresponds the point lambda. And let me give you an example. As you know, like my factors will always be slightly off. But I will still give you the SU2 example just to see how it goes. So so we take the character of the SU2 representation with index m. That's the formula that we will use in class time, and there the parameter was denoted by theta. So according to the scaling law, I should divide it by capital N. And I remind you, this is sine of nm plus 1 nm plus 1 times theta over n. And then this is divided by sine theta over n. So as you see, when n is large, it behaves in the following way. Here in the denominator, in the numerator, you will have sine of m theta, right? Because this one, it will eventually die out. So it will be divided by theta because sine of theta over n will be approximated by theta over n. And this will be times n. I divided by 2 pi and I multiplied, sorry, let me write it this way. So I divided by 2 pi and I multiplied by 2 pi. And that's up to a factor of 2, but sorry, my factors are always wrong. That's the orbital integral for SU2, the integral over a 2-dimensional sphere of radius m. So here that's just a manifestation of this of the general principle. And of course here then there will be some corrections. So in fact, as I say, the Kirchhoff character formula, that's a better tool because that's an exact equality between some geometric object and some algebraic object. So this asymptotic formula upstairs, it's a much less precise tool. But it will turn out that at the present situation with our knowledge, in the infinite dimensional example that we'll be looking at primarily during the second hour today, we can still make sense of the asymptotic formula. We don't quite know how to make sense of the Kirchhoff character formula. So that's maybe our lack of knowledge. That's why we are interested in the asymptotic formula, but who knows, maybe one day we come back to exact equalities. Right. So this was essentially a comment, an extra feature of the material that we saw last time. So now I would like to dive in a new material, and actually our topic, so this will be a new new paragraph. So we say paragraph 4. So we were looking at coadjoint orbits, and we had some very simple examples. Now we'll look at somewhat specific situation, and there we'll introduce our main example of today. So, and it goes under the name of central extensions. Coadjoint orbits. So I'll now specify to some particular case of Lie algebras and Lie groups. And there will be more information about the coadjoint action and on the structure of coadjoint orbits in that case. So as usual, I look at small g. A Lie algebra, let's say we always do things over reals. And I remind you the notion of the Lie algebra cohomology, or more explicitly, a cohomology group H2 with values in the trivial module R. If you don't know these words, don't worry. So here I give you a definition. So these are elements of the second exterior power of G star, which have the following property. When you compute alpha for a triple of Lie algebra elements, so you take a Lie bracket in the first entry and just the third element in the second entry, and you add cyclic commutations, you would like to get 0. So that's the space of cocycles. Now, in the definition of cohomology, you should divide by coboundaries. And coboundaries look as follows. So alpha of xy is equal to beta computed on the Lie bracket of x and y. And here beta is an element of G star. So suppose we have a 2 cocycle alpha on the Lie algebra. So alpha A2 cocycle. So then we can define a central extension of G by a real line, and I denote the generator of that real line by C. So I define a short exact sequence of Lie algebras, and I'll now give an explicit description of this G hat. So in fact, as a vector space, this sequence always splits. So G hat is simply a direct sum of G and that line RC. So what I need to do, I just need to tell you what is the Lie bracket of G hat, and I write it on a pair of elements. So x and y are elements of G, and then a and b are real numbers. So these are just arbitrary elements of G hat. So the Lie bracket in G hat is simply equal to the Lie bracket in G plus. So these guys are central by definition. So that's a central extension. So the Lie bracket of C is everything is 0. So those guys simply disappear. And here I'm adding alpha of xy times C. So it's a simple exercise to show that this is indeed a Lie bracket. So is a Lie bracket. And this follows from the fact that alpha is a 2 cocycle. Suggestively, you have that those cyclic commutations of f, x, y, and z in the definition of a 2 cocycle property, and that's why it's responsible for the Jacobi identity for the resulting bracket. Okay, so we would be interested in coadjoint orbits of groups which integrate such Lie algebras. And before passing to the level of groups, let me make the following remark. I have this alpha now, which is a 2-cos cycle, and I define a map which I will call alpha star. So this will be a map from G to G star, and I define it by the following formula. So this is simply alpha computed on X, and I leave the second argument open. So this gives me an element of G star. So fact, which is easy to check. I will now give you a formula for the coadjoint action in that Lie algebra G hat. You know, it's not a very proper notation, but just to distinguish the coadjoint action in G hat and the coadjoint action in G, I will put a hat over the objects which correspond to G hat. So G hat of X plus AC, and I should be acting on some element of G hat star. Now, G hat star, because G hat was a direct sum of G plus RC, I can also represent it as G star plus R times the dual generator that I call C star. So here I should act on some element. So psi is an element of G star, K is a real number, C star is that generator which is due to C. So it turns out that the answer is a joint star X of psi. So that's just what happens in G and G star, nothing changes, plus K of alpha star of X. So that's so the cos cycle changes the coadjoint action, and note that nothing happens to C star. So here C star is simply killed. No trace of C star remains there. So this is now an element of G star plus 0 times C star inside G hat star. Right. So now I would like to lift this story to the group level. Okay, so hat. So as I say, this is in some way a bad notation, and maybe your question reflects this fact. So I have now two Lie algebras in the game. One of them is G, another one is G hat. So I would like to distinguish objects related to G and to G hat. So the coadjoint action of G is denoted by a joint star, and the coadjoint action of G hat is not very properly denoted, but a joint hat star. So that's is it a satisfactory answer? Okay, thank you. Right. Yeah, but as I say, this is admittedly a bad notation. So your question is very well justified. All right. So let's lift. Let's lift our discussion to the level of groups. So, so we would like to see what is the group G hat associated to G, and sometimes, well, here there would be some integrality conditions on alpha, but in our examples this will always be satisfied. So we assume that G hat integrates to a group G hat, which fits now in the short exact sequence of groups. Now this central line integrates to a circle, and so we always have a homomorphism from G hat to G. Now we assume, let me assume that actually topologically G hat is G cross S1. That's not always the case, but again, for our purposes today, that's good enough. And this means that elements of G hat, we can write them as pairs, an element of G and an element of the circle, where Z is, as usual, something like this. So it's a phase. So now I would like to give you an analog of this formula, but now for the group action. So how does the group G hat acts in its coadjoint representation? So I don't know, you have maybe 30 seconds while I'm writing the formula to guess, right? So how this thing would integrate. So some things are really easy, and one thing is slightly surprising. At least when I was preparing the lectures, I certainly knew it, but then I had to learn it again in some way. Okay, so the obvious things are as follows. Of course, there will be still a coadjoint action of G acting on psi. And it is not too surprising that this term now is not touched again. So it was killed by the coadjoint action of the Lie algebra. This means it's preserved by the coadjoint action of the group. And here, let me write it in the following way. Okay. Gamma of G, where gamma is a map from G to the coadjoint space G star, and it interestingly satisfies the following. It interestingly satisfies the following property. So in fact, this is also a cocycle condition. Perhaps I wouldn't write the complex, I wouldn't write the co-boundary, but this is this means that gamma is a group 1 cocycle of G. With values in G star. So, so that's how it looks like. Now, this looks beautiful, but pretty abstract, right? And I would like to give you two examples. One very simple example, and one not very simple example. So the simple example of this situation will be the so-called Heisenberg group. Right. So that's a good question. In principle, it probably depends a little bit what we assume about G. But normally, yes, because the formula for the coadjoint action here, this alpha star, it gives you an infinitesimal cocycle, and gamma should be integrating that infinitesimal cocycle. I think I would, okay, here, of course, this statement would need some proper formulation, but I think if you have two different ones which integrate the same, then at least they should coincide on the connected component of identity. And if we assume that G is connected, then I think they must be the same. Right. So the first example will be the Heisenberg group. And well, here G will be equal to R2, and it's a billion. And actually, this means that I can identify this capital G viewed as a billion additive group. The cost cycle alpha computed on two-dimensional vectors will be x1, y2 minus y1, x2, or cross product of those two vectors, which in two dimensions gives a number. And since the group is a billion, the coadjoint action is simply trivial. So the coadjoint action doesn't change anything. And now I would like to write the formula for the coadjoint cat action. So this cost cycle defines a central extension of the Lie algebra, and I would like to directly go to the geometry of the corresponding coadjoint orbits. So here, for a group element, I should specify the components of my vector, x1, x2, right? That's an element of G. And then I would like to specify, so Z, that's an element of the circle. And I'm acting on psi1, psi2, and here K. So G cat star is isomorphic to R3. So the first components, these are components of an element of G star, and that's the coordinate along this dual to the central line. So where does it go? I did a computation, and actually now I see that I forgot a very, very important element here. Maybe it's actually even good because I should now put it here. So this gamma of G is multiplied by K, and this will be hugely important in our discussions. So maybe that's good that we, and it corresponds to this K here. So I made a computation. I'm not sure, as usual, about my signs, but I got something like this: psi1 plus K, x2, psi2 minus K, x1, and K doesn't change. So that's what typically, of course, here it's all very simple. So this is just a linear transformation, right? And but that's what happens, right? You always have some kind of component which is proportional to that central, that dual of the central element, to K. Let me draw the corresponding coadjoint orbits. So the coadjoint orbits of the Heisenberg group. So I draw my R3 picture, psi1, psi2, K. And a typical coadjoint orbit, as you see, that would be just a plane of constant K, right? So that's a plane of constant K. So you can move, right? You can move using the coadjoint action by translation along that plane. Just for your information, right? The corresponding canonical to form is this. So this is the constant symplectic form times k. In particular, there is a special plane of k equal to 0. So the plane which passes through the origin. And there on that plane, the coadjoint orbits are simply points. And that you can also see, because if k is equal to 0, all of a sudden the symplectic form vanishes. It no longer makes sense. So there is a plane which consists of point-like coadjoint orbits, and all the other coadjoint orbits are horizontal planes with a two-form proportional to k. So that's the last easy example that we look at. And now we introduce a more complicated example of the same construction. And that's the example that we'll be interested in for the rest of this mini course. All right, so our example number 2. So the group will be the group of orientation preserving diffeomorphisms of the circle. Now, maybe in more details, we can write it in the following way. We can think of maps from R to itself, which have the periodicity property. So phi of x plus 2 pi is phi of x plus 2 pi. And since we want diffeomorphisms, we want the derivative to be always positive. Of course, this is an infinite dimensional gadget, but we can still define a Lie algebra which corresponds to it. And this is simply vector fields on the circle. And since we wrote here the periodicity condition, I also write periodicity conditions here. Okay. So of course the Lie bracket X is just the standard Lie bracket of vector fields. Now we need some model for G star. Of course, this is an infinite dimensional space. If I do it properly, I should introduce some topology on it and then define G star, but instead we'll be dealing with some kind of smooth piece of G star. So what I denote by G star, that's a piece of real dual to that vector space. And we define it as follows. So geometrically, this will be a quadratic differentials on the circle, T of x times dx squared. So T of x plus 2 pi is equal to T of x. And you may be wondering why I want to introduce this slightly non-standard gadget, the quadratic differentials. But this is because then tensor calculus gives us a natural pairing between T and V. So this is an integral 0 to pi T of x, V of x, dx. And now this expression is a natural expression with respect to the change of variables. So here we have dx squared, here we have d over dx, and the pairing is a one form naturally, so therefore I can integrate it over the circle. So let me also write a coadjoint action, right? You know that you need a coadjoint action, and I invite you to check it. So that's an easy calculation. T of x, and well, of course, diffeomorphisms would shift the argument. Here again, I must admit, I never know, right? One needs a left action or right action. Should one put f or f minus 1? Let me do the formulas ignoring the subtlety. But if you really want to make it precise, one day you should figure out whether I should put here f or f minus 1. And what is interesting, because I have dx squared, when I make the change of variables, I should also multiply by the factor, which corresponds to the fact that this is a non-trivial tensor on the circle. Of course, tensors on the circle, that sounds a little bit trivial, but that's how it looks like. So that's the coadjoint action. Now, what about the central extension? Maybe before doing that, I introduce one more piece of notation, which would bring it closer to what people are used to in the physics literature. So let me introduce a complex coordinate on the circle, and let me write the following complex value. The following complex values vector field denoted by Ln, which is minus z to the power n plus 1 d over dz. Of course, here I'm always thinking that z is that function of x. So these are complex valued vector fields on the circle. So then the Lie brackets for those generators are given by that formula. Now there is a famous theorem which classifies two co-cycles on this Lie algebra. So it says that there is a unique equivalence co-cycle on G or on GC equal 1. Oh, okay. So let me get back here. So this is for mathematically minded part of the audience. Truth be told, if you have that infinite dimensional space G, you should say what is the topology on that space, and then consider G star as a space of smooth linear functionals on G with respect to the topology that we fix. I mean, typically that would lead to two things. Either if I take G to be reasonably nice, then G star will be huge, will contain some really wild objects, or I should admit some kind of relatively wild, or at least not really smooth objects in G. I don't know, introduce some Sobolev space or something, and then G star will become reasonable, but also not smooth. So since I'm not that much interested in that part of the story, maybe at some point I mentioned something, but I prefer to work with smooth objects everywhere, so everything is nice. But then these smooth T's, they make only a small part of the true G star. So that's why I put quotation marks. So this is a smooth, or whatever, the subset of G star that I'm interested in. Is it a good approximation of an answer? Okay. So we return to the Biggs theorem. So there is a unique arc to equivalence to cocycle. So there is a unique arc to equivalence central extension. And of course, up to a multiple. You can always multiply your cocycle by something. And I'll write two formulas for it. So one formula will be up to a multiple, and you know I'm bad with multiples. But then the other one will be more precise. So alpha is proportional to the integrals of u times the third derivative of v. But let me fix the multiples again by the conventional formula. I computed on those generators ln and ln, and well, the convention is to put 1 over 12 delta m plus n 0 and here m cubed minus m. So the complexified version of the resulting algebra is called the Virasoro algebra, and that's one of the most important and most famous objects, probably in the whole of mathematical physics. So we have GC, this extension is Virasoro, and so that's the Virasoro algebra. And just to write relations, well, I guess probably 100% of you saw them many times. But I mean, we just combine the two formulas on the upper blackboard, right? So this will be a and yeah, let me write it. Yeah, so we saw it hundreds of times, but now let's write it explicitly. What do I want to do? The one with 12. 0 m cubed minus m times t. Right. Okay. So that's the. So these and c is central. All right. Now, when you restrict to G, the central extension would integrate. Restricted to G. It integrates to the exact sequence of roots. And we would like to describe, we would like to study, we would like to talk about coadjoint orbits of this gadget. So, so the question is, study coadjoint orbits of this gadget. In principle, perhaps at this point, I should give you some motivation why this is an interesting question. but perhaps let's postpone the motivation to the end of the mini course. So that's partly because much of the motivation comes from physics, and I don't 100% master those things. So towards the end, I will show you, at least I repeat some of the words which provide, I think, sufficient motivation for the study. But that's the thing which involves naturally mathematically. Of course, you see now diffeomorphism of the circle. That's one probably of the first examples of an infinite dimensional group that you can think about. It's a nice one. And it turns out the Virasoro, it plays a huge role in mathematical physics. So that's the basic of conformal fields theory. And there are further motivations to study this story. So now let me give you the expression for gamma. Recall that the important point, right? The important point in this story is this map gamma. So let me see whether I can keep it here. So gamma is supposed to be a map from D plus S1, and it should be sending it to G star, right? It should be sending it to this space of quadratic differentials. So, I mean, what is it? So the formula is explicit, beautiful, scary, surprising. I don't know, probably many of you have seen it, but maybe not all of you. So, and I will write here T of x. I don't write the x squared. So a diffeomorphism F is mapped to some element of G star, which is T of x. And this T of x is given by the third derivative of F divided by F prime minus 3/2 F double prime divided by F prime, and this is squared. So I mean, I don't know. I imagine I hope some of you never seen that expression, because if you did, of course, it's not surprising for you. But if not, then wow! I mean, well, how? So this comes by integrating that cocycle. So you convert the cocycle into the one cocycle with values in G star. You integrate it. That's the result. So this is known as the Schwarzian derivative. So an exercise check cocycle. Check cocycle property. Remember, gamma should satisfy some equation, and of course, for a composition, right? Gamma of a composition should be expressed in simple terms as gamma of the two parts. Of course, at the moment, it doesn't look plausible, right? So you need to compute it, and you need to see that it actually works. At the moment, like, imagine you substitute instead of F a composition of two maps of F and G. Well, I mean, it shouldn't work, but it does. Okay, maybe before we leave this topic and go to the classification of coadjoint orbits. So let me do two things. First of all, let me state more precisely how the coadjoint action looks like. Now we know gamma, we know how the coadjoint action before a center extension works. So coadjoint action of plus S1 cat So again, let me not write dx squared. So f sends t of x to c of f of x, f prime of x squared. So remember that was the easy part, but now plus, and here we should take this k, and I think the convention is that we should divide by 12, but you know, this is really the convention, this is 12. And you multiply by this S of F gadget. So that's the coadjoint action, and we will be classifying orbits of that action, and then we will be doing other things with those orbits. So maybe the last thing before the break, I unfortunately erased, but let me write again this formula. For the Versor algebra. So we will be interested in some least algebras of this guy. And the first remark is that, of course, if we take C times L naught, this is an abelian least algebra, obviously.
Actually, the notation S of F we introduced instead of S with X.
Oh, yeah, that's right. The standard notation for the right-hand side is S of F, S for Schwarzen. Sorry. But then, interestingly, there are other subalgebras. So it's easy to check that L naught, L plus 1, and L minus 1 generate SL2C. And also Ln, L minus n. And let me write it this way. The Lie bracket of Ln and L minus n, which is some linear combination of L naught and C. Right? It's also isomorphic to SL2C. So for n greater than equal to 2. So, and in fact, if you restrict those subalgebras to the real part, to G, so here I wrote them as subalgebras of GC, but the real parts will be just one-dimensional abelian subalgebra will be SL2R and will be SL2R. So I have a distinguished or the simplest abelian subalgebra, and I have many SL2Rs which are indexed by n, and we're going to use it in the classification result just after the break.